Greetings of the day to all of you. Today we are going to resume lecture 3 on applied power electronics, where we will continue with module 1, that is the device structure and characteristics. And in continuation with our previous lecture, where we had discussed power diode and its structure and operation, followed by a silicon control rectifier or thyristor with its structure and operation, we will now move on to fully controlled devices in this lecture, that is power MOSFET and IGBT. So let's move on to power MOSFET, which is basically metal oxide semiconductor field effect transistor. If you know from analog electronics, the courses that you have had on analog electronics in your undergrad, a MOSFET is basically a 3-terminal device. Let's talk about an NPN MOSFET, particularly about the enhancement type MOSFET, because the enhancement type MOSFETs are the ones that lay the foundations of design for power MOSFETs. So basically power MOSFETs are all enhancement type MOSFETs. It will have a silicon wafer. I'm talking about a normal signal MOSFET that you have studied in analog electronics. We're just doing a quick recap of that, so then we can build up towards power MOSFETs. So a low rating MOSFET has a silicon wafer over which a certain region is doped with N-type, is doped as an N-type region. That is, it is doped with the, say, phosphorus. And then you have a p-type region doped with, say, boron, and then you have another n-type region somewhere over here doped again with a valency of 5, say phosphorus again. Now you have this terminal is known as the drain, the top n region, and the p region is known as the body, and the bottom N region is known as the source. Very often in the construction, there is a body source short by means of a metallic contact. So the body is shorted with the source by means of some metallic contact. The other side of the body over here has the gate terminal, obviously with the help of an insulation between the gate terminal and the p-type region through gate oxide. So this is insulated. I'd like to show it with diagonal lines, so you know that this stands for the insulation. So this insulation of a gate oxide ensures that there is no direct metallic contact, no direct conductivity between the gate and the p-type body on this side. Now when we give some positive potential to a MOSFET, positive potential of the drain with respect to the source, at that time it looks like no flow of current can take place, because essentially if you see, this PN junction is reverse biased, so it is not going to allow any flow of current. But what happens is that once you give some positive potential and then you also give a gate, you give a gate voltage with respect to the source, so this gate terminal becomes positive, although it is electrically isolated, but because of the positive potential, the effect of a field is created. That's why we call it a field effect transistor. An electric field like effect is created over here, and all the minority carriers in the p region, that are your electrons, move closer towards this positive terminal of positively charged terminal. So all the electrons, they are very few because they're minority carriers in the p region. They might be very few electrons here, but the holes, which are let me show the electrons with negative charge, but the holes, which are which are large in number, are vacated from this region, and they move away from the holes, start moving away to the other side of the wafer, and they move away from the positive gate. So what is left behind is the immobile negative charge, because the holes have been vacated, and the minority carriers, that are the electrons, if they have come from the major portion of the wafer towards the positively charged gate. So few electrons, that are your minority mobile carriers, and immobile negatively charged particles which already existed. So this sets up a channel between these two n regions in an enhancement type of MOSFET, and an N channel is set up, so you have a continuous flow of electrons from in this region, connecting the drain and the source directly. So now when you give positive potential, when you have given a positive potential, obviously all the electrons have a smooth conducting path through this N channel, and they can move into the drain, which is positively which has a positive potential. And obviously if electrons are moving from the source to the drain, it means the flow of current from drain to source is established, because that's obviously the current flow of current is always opposite to the flow of electrons. So this is how we set up current flow from the drain to source. So this was about a simple MOSFET. Now if we extrapolate this information and we want to design a power MOSFET, which is basically a MOSFET, the same thing, but it is available in high voltage ratings. That means it can block very high positive voltages, and it is supposed to conduct very high magnitude currents. Obviously I told you when we were discussing power diode, that time also I told you that the constructional difference between power level devices and signal level devices are that they have very thick wafer dias, which allows high current carrying capability of these devices, and often power MOSFETs are vertically mounted in order to enhance their current carrying capability. Apart from that, in a power MOSFET, we have an additional N minus region. Let's see how a power MOSFET looks like. So you have a drain, and you have say a highly doped N plus region, and down there it is an N minus region, which is often known as a drift region. On this N minus region, we have some P regions doped, and then there are again highly doped N regions somewhere here, like this. So it is again an NPN structure, but some structural modifications are done to enhance the current carrying capability. Basically you are increasing the current paths, providing parallel paths for current to increase the current carrying capability, and you are incorporating an N minus layer so that your depletion region can penetrate deeper and deeper, and it will give you high voltage blocking capability. Now this is your drain, and this portion, the N region over here, is your source, and the source region is shorted with the body region, that is your P. The P is your body region. It is shorted, the body source short is present again. And this forms your source terminal, say S. So you have the drain, you have the source, and this remaining body portion is insulated through gate oxide, and this forms your gate terminal G. Now let's see, when we give some positive potential to the drain with respect to the source, so it's a forward bias condition. Let's see what happens. It looks like that this PN junction is reverse biased, so it is obviously not going to conduct. So there is going to be a depletion layer that is going to form over this junction and this junction. And because of this depletion layer, as we go on increasing the forward bias, this depletion layer will go on penetrating into the N minus region, which has been created in a power MOSFET. It does not exist in a signal MOSFET, the N minus region, but there is uniform doping over the N region in a signal MOSFET. But in a power MOSFET, the N part, which is closer to the PN junction, is lightly doped, so your depletion region can penetrate deeper and deeper, as a result of which you have high forward voltage blocking capability or high positive voltage blocking capability. So that's how you're increasing the voltage blocking of the MOSFET. Now, in order to make it conduct, you have to give some potential at the gate, some voltage at the gate. It is a voltage control device. You're not injecting gate current, but you're giving some voltage across the gate source terminals. You cannot inject current, it is insulated, but you can definitely give potential over here. Due to positive potential over here, what happens is that all the electrons, the minority carriers of the body region, come over here, the minority carriers, and all the holes move away. As a result of which, what is left behind is the immobile negative charge. So basically, you have set up a channel between this N minus region, and this N plus region. N minus region, which is also known as a drift region. So you are setting up a channel between the drift N minus region and the source N plus region through the body, which is the p-type region. So this is your N channel over here, and this is another N channel over here. So if you observe from the drain to the source, there is a continuity of N channel. So you have a continuous channel for the flow of current. If the drain is positively charged, then obviously electrons will flow along this channel and they'll be injected into the drain, or in other words, you can say that there is flow of current from drain to source once you have injected a gate, once you have subjected it to a gate voltage, a sufficient gate voltage. So if we revise what we had already done about studied about the characteristics of a MOSFET, if you have to block voltages, we know that it can block positive voltages like this. So it has blocked positive voltage. Unless you don't give it a gate, it will not conduct, because this PN junction was reverse biased and there was no channel and there was no conduction path. So obviously it was blocking very high magnitude of positive voltages, because this was N minus where depletion region could penetrate. And then when you carried current, you can carry forward current from drain to source. So if you see ID, it can go positive direction. If you remember our previous lecture, the first lecture for that matter, you would know that the MOSFET can also carry negative currents. Let's see what happens when we give a negative voltage to this power MOSFET. So if I make the drain negative and the source positive, let me go back. If you see this, the source body short, which means that the p-type body and the n-type source are shorted. It means that the source potential is brought at the p point, at the body point. And whenever I give a positive terminal, I give a positive voltage at the source, this p-n junction, it appears like, the source is directly connected, this positive terminal is directly connected through the short to the body, to the p-type material, and the drain here is connected to the n-type material. So you're forward biasing this p-n junction, and you're basically bypassing this p-n junction, which would have been reverse biased. So essentially, due to the source body short, this positive point is brought here, and you can see that this is nothing but the body diode of the anti-parallel body diode of a MOSFET, which I had told you in that lecture that a MOSFET inherently, because of the body source body short, the MOSFET inherently has a diode in its reverse path. So this diode will automatically go into conduction because it will get forward bias. So it does not have a reverse blocking capability. It cannot have reverse blocking capability, but it does have reverse current carrying capability, because once you give it a reverse voltage, it will start carrying current in the reverse direction. Through this path, through this PN junction. But I also told you in the first lecture that it is generally not used to carry negative currents, because if you see, this body diode has to carry current through the Pn minus region. The N minus region has less number of carriers, and when it has less number of carriers, its on state resistance is high, as a result of which it is a lossy path for the current to go through. When it has to take the reverse direction to go through the body diode, it is it'll produce more drop. So generally what we do is we connect fast recovery diodes across MOSFETs. If we have to make them carry negative currents, we connect an additional fast recovery diode across them, which does not have this problem of N minus region, and then they quickly go into they can carry currents in the negative direction without producing much losses, without being too slow. They're very fast devices. So this was about a power MOSFET, where we have N minus region again for increasing the voltage blocking capability, and to give control to the device, we have a gate terminal which helps us in setting up an N channel for the device conduction. And for the reverse the device does not have any reverse blocking capability, because once you reverse bias it, the inherently existing body diode in the device, which is basically inherently present because of the body source short, that automatically goes into conduction and it starts carrying current in the reverse direction. So this was about the power MOSFET, which is basically a MOSFET at high voltage blocking capability and high current carrying capability. Like I said, it has thick wafer diodes and it is vertically mounted to increase the current carrying capability. Moving on to the other device, which is your IGBT. This MOSFET you can study from Ned Mohan, and also there is an application note from International Rectifier. I'll just write the note, application note number on the group once I share the video with you. Moving on to insulated gate bipolar transistor IGBT. Again, it is a fully controlled device. We already know that. And it is again controlled through voltage, where we control the gate emitter voltage of the IGBT to turn it on and turn it off. It is quite similar to the MOSFET in terms of its controllability, but it comes in much higher voltage and current ratings as compared to the MOSFET. Now the structure of an IGBT is has 4 layers, PN again, but it is just that the doping concentrations are different. So you generally have P plus, N plus regions, which is also split into an N minus region. Let's move to the construction. You have, let's call it a drain for now. You have a drain region, which is basically the collector region. When you talk about an IGBT, you can call it drain for now because we've just studied the MOSFET and it's easier to use the same terminology. But for an IGBT, the term collector is usually used. So you have a P region, pretty highly doped, P plus, followed by an N region, which is highly doped, and it is known as a buffer region. Not all types of IGBTs have this. Some have it and some do not have it. And those IGBTs which have this N plus region, they are known as a punch through type IGBT. It is generally advisable to have the N plus buffer region. And then you have an N minus region. So you have P, N, and then you have another P, a big P region, and then finally some N region again. Alright, so you must be pretty aware that this N minus region is there so that this PN junction can tolerate very high reverse bias. It must be clear to you by now. Now, again, this P region is your body region. This N minus region is known as the drift region. And this is your source. And again, you have the body source short. the body and source are shorted, so this makes your source terminal, or you also call it the emitter terminal, or E, which I have denoted with E. So the drain and collector are interchangeable, and the source and emitter over here are the interchangeable terminologies. Now you also have the gate terminal over here, which is again insulated, as the name itself suggests, very similar to a MOSFET, that the gate is insulated through gate oxide and it is connected near the body, which is, this is one common terminal. I don't have space. This is one common terminal which I will call as the gate. Okay. Now what happens is that once we give some forward bias, say the drain is positive with respect to the source, what happens is that the first junction J1 becomes forward biased, because this P region is connected to the positive side. But this particular junction, if you see this junction, let's call it J2, it is reverse biased. Although the third junction, that is J3, very similar. Can you see similarities with thyristor actually? J3. So if J1 and J3, we talk about these two junctions, they are forward biased, but junction J2 will be reverse biased even when the whole device is forward biased, as a result of which it will not go into conduction, but it can tolerate high magnitudes of positive voltages, which are basically reverse voltages for this particular junction, because this junction is made of a drift region with an N minus low concentration of carriers over here. So the depletion region can penetrate deeper and deeper. In certain cases, you may not have the N plus region also, which I told you, which is a non-punch through type of IGBTs. They may not have an N plus region, and the entire thing could be just an N minus region. Those kind of IGBTs even have reverse blocking capability, reverse voltage blocking capability. But anyways, for now we know that when we give positive voltage to this IGBT, it is not going to conduct, it is going to block this positive voltage because let me call it collector emitter, because I have not given it any gate as of now, and one of the junctions is reverse biased. Now what happens is that if I give some positive potential at the gate, it's not injection of current, but it's just putting voltage across the gate emitter terminals and not injecting current, because the gate is actually insulated from your main wafer. But because your gate is positively charged, and because of that an electric field is set up, so all the minority carriers of this P region, that is your body region, all these minority carriers, the minority carriers in these regions are the electrons, very few in number, but they do exist. They come closer to the gate. So there are a lot of electrons over here, and the holes move away from here, leaving behind immobile electrons. So again, if you observe, you have a channel setting up here. So if you see from the source, there is N region, and then there is a channel, and then there is the drift region again, and then again the N region, and then at the top you do have a PN junction, but that is forward biased, and that's not creating any trouble for you to conduct. So conduction will begin in this direction from P to N. There will be a flow of current, and then obviously through these N channel, through this N channel into the emitter, you have flow of current. So positive current can flow through an IGBT. You cannot make negative current flow through an IGBT, because like I said that there are three junctions, J1, J2 and J3. If you reverse bias it to, there are two junctions that will be reverse biased, negative current cannot flow, and it cannot block negative voltages. Some types of some types of IGBTs, which are known as reverse blocking IGBTs, they can block reverse voltages. Those IGBTs do not have an N plus layer generally, and they do not have a buffered layer, and they are known as non-punch through type of IGBTs. So this was about an IGBT. If you observe one more thing, it's very similar. It has a parasitic thyristor, if you observe, because it has essentially just like a thyristor, it has 4 layers, PN, PN. So if you see from the drain to the source, there is a parasitic thyristor in the IGBT structure itself, and you do not want that parasitic thyristor to be triggered unnecessarily, because you want it to behave like an IGBT. But for that, if you see the gate as the body source short, which essentially shorts the body region with the end region, that body source short differentiates it from a thyristor, और वो इस parasitic thyristor का turn on prevent करता है. It is not desired that this parasitic thyristor should turn on. It is desired that when you give some potential at the gate, only then it should turn on, and when you withdraw that potential, the channel will vanish and it will turn off. So that is about your IGBT. I've briefly discussed these points. I've not gone into many details because I believe that this much is sufficient, that you know that how it is a voltage control device and not a current control device, or how it can block positive voltages and carry only positive currents. Basically, understanding the basics of their operation. In the next lecture, we will move on to a little bit information on some modern technologies and devices like a wide band gap power electronic devices, and a little bit on modules and IGCTs. And with that, we'll wrap up our module 1. I'll share the application note number, and apart from that, you can refer to Ned Mohan, which is a pretty decent book on device physics. Let me know when we can schedule the doubt clearing session. Wishing you all the best. That's it for today.